For this graph, this is a rational expression, and we have a lot going on here. So what I always want you to do is kind of follow this general, outline of what we're going to do in this example when you're doing this on your own. So I always want you to factor first. So this is already factored. So step one, already done. But I always want you to factor first. Okay. Next, we are going to look for our holes. So holes are a discontinuity. So discontinuities are going to include holes and vertical asymptotes. So we're always going to start with the holes. Always, always, always. So the holes are when you have 0 over 0. So what value of x gives you 0 over 0? Well, you'll notice that if you plug in 2 here and here, you would get 0 divided by 0. So we have a hole at x equals 2. So the reason that we want to find our holes first is it's basically what you can cancel in your numerator and denominator, and that kind of gives you where the hole is going to occur. So again, it's the x value where you can get 0 over 0 for a rational expression. So that's at 2. And then to find the y coordinate of the hole, you are going to plug 2 into the simplified function. So now I have 2 squared, so that's 4 times 2 plus 3 is 5 over 2 plus 2 is 4 times 2 plus 1 is 3. So that is 2 comma 5/3. So I know I'm going to have a hole at 2 comma 1 and 2/3. So right about there, I'm going to have a hole. Okay, the next thing you're going to do is find vertical asymptotes. Now, vertical asymptotes occur when you have a number that's not 0 divided by 0. So for example, if I plugged in -2, my numerator will be 4 times -1. I'm sorry, 4 times 1. So my numerator would not be 0. But if I plug in -2 into my denominator, I would be dividing by 0. So it's the number that makes just your denominator equal to 0, but not your numerator. And that's why you want to start with holes, because then you can just ignore the holes if they cancel out. And in this case, we only have x minus 2 and x minus 2, so they totally cancel. So now I know I'm going to have a vertical asymptote at x equals -2 and x equals -1. And you'll notice that I wrote them as x equals. That's because they are equations. Vertical asymptotes are equations of vertical lines. So write them as the equation of a line. Don't just write a number. It's not just -2. It's x equals -2. All right, and then our zeros, okay, well, that's what makes your function equal to 0. So 0 divided by any number that's not 0 is equal to 0. So for example, if I plug in 0, I would get 0 times 3, so that's 0, divided by 2. So 0 divided by 2 is 0. So your zeros, or your x-intercepts, occur with whenever your numerator, and just your numerator, is equal to 0. So that would be at x equals 0 and at -3. That's when those are the x values that make just your numerator equal to 0. Okay, so I'm going to graph those up. 0, 0, and -3, 0. All right, and then the general end behavior function. So I do not really cover finding the actual end behavior function. That should have been covered in your pre-calculus course. So finding the actual end behavior function will require long division or synthetic division if you can use synthetic division. On something this complicated, synthetic division wouldn't be enough. You would have to use long division. But for this class, all that you really need is the general end behavior function. So to find the general end behavior, so it's not the exact end behavior function, but to find the general end behavior function, FN, I'll just say that's function. This is what you're going to do. You are going to look at your leading term in the numerator and the leading term in your denominator. So my leading term would be x cubed for my numerator. And my denominator, it would be x plus 2 times x plus 1. My leading term would be x squared. And I want you to find the entire leading term. So like, let's say there was a negative on the outside. Then my denominator would be -x squared. So make sure you include any coefficients, okay? include any coefficient. So the general end behavior function in this case will be y equals x cubed over x squared. Well, that's y is equal to x. So my general end behavior function tells me generally, so not specifically, generally, what my end behavior will look like. Well, okay, what does y equals x look like? Y equals x is a line with a positive slope. And that's all I really need to know. It's a line with a positive slope. So that means at the ends, my graph will generally be a line with a positive slope. And notice that I only graph it at the ends. That's because it's end behavior, not middle behavior. So you will not see me graph a horizontal asymptote all the way through. You will not see me graph a slant or an oblique asymptote all the way through. So let's pretend, like let's say I had another example where I had like x to the fourth over negative x squared. Well, x to the fourth over negative x squared would be negative x squared, right? So if this was the example, then my end behavior would act as a negative x squared. Well, negative x squared is a negative parabola, so my ends would both go down because that's what the ends of negative x squared do. So the general end behavior function, again, it's just a way to get your end behavior, but not have to go through the whole process of doing long division. It's just an idea of what your graph looks like. And my graph isn't going to be exact anyway. So this is what I want from you when you're graphing. And then we're going to go ahead and fill in our graph. So you're going to start on the right side. You're going to follow your end behavior function. And then, okay, I see a hole. I have to jump over the hole. I see a 0. I have to cross the x-axis at that 0. I cannot cross the x-axis anywhere else. You can only cross the x-axis at your bridges. I call them bridges, and this is a river. Okay, you cannot cross the river without a bridge. Okay, now at this particular bridge, it's squared, so that's an even multiplicity. If you have an even multiplicity, then that means you stay on the same side of your map. Okay? Anytime you have an even multiplicity, you're going to stay on the same side. So I can't actually cross over. I'm going to stay on the same side. And I'm not allowed to cross a vertical asymptote either. A vertical asymptote is like a magical infinite wall. Okay? You cannot jump over it. It's infinitely tall. So I can only go up and approach the asymptote. Notice that I cannot go down because then I'd be crossing the x-axis without a bridge. So I go up, okay, and I approach my vertical asymptote. Now, this vertical asymptote has an odd multiplicity, or in other words, it doesn't have an even multiplicity. So I transport to the opposite side. If it was x plus 1 squared, then I would stay on the same side. Okay? So if it's an even multiplicity, again, you stay on the same side of your graph, but because it's an odd, I transport to the opposite side. Okay, now, in between these two magical walls, do I have any bridges? No, I do not have a bridge. So I cannot cross the x-axis. So the only thing I can do is turn around. I can't go up because then I'd be crossing the x-axis, so I have to turn around. Now, where do you turn around? It doesn't matter. I wouldn't go all the way. You don't need to go all the way to the river's edge to see you don't have a bridge. I can see don't have a bridge way down here, so I'm just going to turn around. We'll learn more about where turnaround points are and get actual points when we get into more complicated calculus. But for now, just turn around somewhere. It's just a general idea of what this graph looks like. And then I transport to the opposite side because, again, this does not have an even multiplicity. So I just transport to the opposite side. And then, I do have a bridge. I can go through this bridge. And then, my end behavior function is down here, so I follow my end behavior function. Okay? So you need to know a lot for these types of graphs. You need to know how it works if you have a hole. You always have to show your graph jumping over that hole. Okay? We would not do anything like where we skip over it. We are always jumping over the hole. Your zeros with even multiplicities, you bounce off of. Your vertical asymptotes, you never touch, you can only approach, and they always go to infinity or negative infinity. You transport to opposite sides if it's an odd multiplicity. You stay on the same side if it's even, but that didn't happen here. And make sure you are following your end behavior function on both ends. If you were to end up here, you would know that either your end behavior function is wrong or something else is wrong on your graph. Like maybe you bounced off an x-intercept when you weren't supposed to. or you ended up on the same side of your vertical asymptote when you weren't supposed to. So if the end of your graph does not match with what you know the general end behavior function to be, either your general end behavior function is wrong or something else is wrong and you need to go back and fix it. So that's what's also nice about the general end behavior function, is it kind of gives you like, oh, I ended where I'm supposed to, so I'm pretty sure I didn't make any other mistakes. You would have had to make 2 mistakes to end up at the same place. If you made 1 mistake, you would probably end up in a totally different place.